All right, looking at the last method here, it's called Simpson's rule. Some dude named Simpson came up with it. Okay, so it's the same kind of thing. We're still going to be doing these approximates for the area under the curve, but instead of doing trapezoids this time, now we're going to approximate using parabolas. I looked in the book for a picture, and I didn't really like the picture too much, but here it is. So basically what we're going to be doing is, again, we're going to be partitioning the interval from A to B into a bunch of different partitions, but instead of doing the trapezoidal areas, we're going to be doing a parabola as the area. Now, there's a really complicated background to this. If you want to look through the book, which I would recommend looking through on how this works, I'm just going to write out the formula, though. So for Simpson's rule, we almost always label this with an S. The formula for this one, and it's very similar, is this. So it's going to be delta x, but this time over 3, times the first y value, y sub 0, plus 4 times the next one, plus 2 times the next one, plus 4 times the next one. And it's just going to alternate 4, 2, 4, 2 all the way down until it's 2 times the n minus 2 y value plus 4 times the n minus 1 y value, and then just a single y sub n on the end. Okay. So it's always going to alternate 4, 2, 4, 2, 4, 2, where it starts off with 1 as the coefficient, and it always has 4 as the next one and 4 as the second to last one. To make that happen, you always need your n value to be even. So when you do cut up your partitions, you have to cut them up into an even number of partitions. Let's do the same thing that we did before. We're just going to jump straight into an example. Let's look at the example from 0 to 2, 5x to the fourth. Oh, come on, you. dx. Okay. Cool. So again, just kind of jumping straight into Simpson's rule here. This time, my interval is going from 0 to 2. We're going to use 4 partitions again. If I'm cutting up the area from 0 to 2 into 4 different partitions, that means that each one of those partitions is going to have a length of 1/2. So we're just going to jump straight into the formula. So my delta x is going to be 1/2. I'm going to take that 1/2 and then divide that by 3 times these different y values. So I'm not going to write this one all out like last time. Let's go ahead and just plug it all in. So it's going to be our function 5 times the value 0 to the fourth. All right, so that's the first one, plus 4 times the next one, which is going to be 5 times the next value up would be 1/2 to the fourth, plus 2 times plugging the next one in, which would be 5 times 1 to the fourth, plus 4 times the next one, which would be 5 times 3/2 to the fourth, plus the last one, which does not have a coefficient out in front, it would just be that 5 times 2 to the fourth. Okay, so plug all of this into the calculator. I'm not going to bother doing it on screen here. I'll pause it and do it on my own. Okay, so I got 32.0833333 when I plugged it all into the calculator. Just real quick to compare that to the actual answer. The actual answer for that integral up top is 32. So again, I hope you can see how close we were. And we can find the error percentage here. So if I take that 32.08333, subtract that by 32, and then divide by 32, this time I have an error of 0.26%. So you can see it's a little bit better than the one that we did up top. We did 0.446%. Now it's 0.26%. So Simpson's rule is a little bit better than the trapezoidal rule. Okay, we're not done with this section. Those are the 2 techniques we're going to look at, trapezoid and Simpson's. What I really care about, though, is I really care about something called error analysis with these. What error analysis allows us to do is kind of do the question, but in reverse. Instead of using the trapezoid rule or the Simpson's rule to find the area under the curves, what we're going to do is we're going to set what we want the error to be, or at least what we want the minimum amount or the maximum amount of the error to be, and then we're going to find the number of partitions we need to get that error. There's 2 formulas that we need here, and I'm going to have to pause it and find them in the book so we can write them down. Okay, so these are the 2 errors here in Theorem 1. We have the error approximation for the trapezoidal rule, and then the error for the Simpsons rule here. They're very, very close formulas. So just to read through it here, the absolute value of the error using the trapezoid rule, which we label E sub t, is less than or equal to m. We'll talk about the m here in just a second. B minus a, the b and the a are the upper limit and the lower limit of your interval, that cubed, divided by 12n squared, where again n was the number of partitions. All right, so the m is probably the hardest thing to find here, so let's talk about that. The m in this formula for the trapezoidal rule represents the upper bound of the absolute value of the second derivative of the function. So we'll do an example, we'll kind of talk about that. Simpson's rule is very similar. It's pretty much the same formula, just some of the numbers have changed. But here the m represents the upper bound of the fourth derivative of the function. Okay. So let's go back and let's look at some examples. This is the stuff I'm going to be asking you to do. Estimate the number of subintervals needed to approximate the integral. And here we're going to do the integral from 0 to 2 of that 5x to the fourth. So the same thing that we were just doing using Simpson's rule. With an error of magnitude less than 10 to the negative 4. Okay, this is pretty much exactly how the question is going to be worded on the homeworks, quizzes, tests, and all that. So estimate the number of subintervals needed to approximate the integral from 0 to 2, 5x to the fourth dx using Simpson's rule with an error of magnitude less than 10 to the negative 4. So just to remind you of the formula for Simpson's rule, the absolute value E sub s is less than or equal to a big fraction, m times b minus a, this was to the fifth, I think. That divided by 180 into the fourth. So let me just double check real quick. Yeah, we're good. Okay, so here's the formula, and here's how you'd want to use the formula for a question like this. First things first, it's asking for the error of magnitude to be less than 10 to the negative 4. So what we're going to do is we're going to take this entire equation and bound that from above 10 to the negative 4. So it's going to be this thing on the left, and that's going to be less than or equal to that 10 to the negative 4. 10 to the negative 4 is 0.0001. You just move that decimal place 4 stops to the left here for scientific notation. Okay. Let's look at that m value. So let's find m. Remember, to find m for Simpson's rule, we have to find the fourth derivative of the function. All right, so let's do that. The original function is 5x to the fourth. Let's take the first derivative. First derivative of that would be 20x cubed. Second derivative, bringing the 3 down, would give us 60x squared. The third derivative would give us 120x. Fourth derivative would be just 120. Okay, so this one's very easy because this time we got our fourth derivative just to be a constant number, but it's not always going to be a constant. No matter what the fourth derivative is, you want to find the maximum of that function on the interval. So if we're looking at the interval from 0 to 2, just figure out where this function has its maximum. Of course, this is just a constant, and because it is just a constant, the maximum value is just that value, 120. Okay, so now we're going to plug all that stuff in. We're going to take that 120 for the m times b minus a is going to be 2 minus 0. Remember, those are the lower and upper bounds for the limit. That's to the fifth, all divided by 180, and then n to the fourth. We do not know what the n is because that is actually what we're trying to find. All right, so remember, like I said, we're going to bound that by this 10 to the negative 4, which is 0.0001. Now just solve for that n to the fourth. So we're going to multiply the n to the fourth over to the right-hand side and then divide by that 0.0001. All right, so we get this. On the left-hand side, we're still going to have that 120, still going to have that 2 to the fifth. We're still going to have the 180, and now we've just divided over that 0.0001. and we multiplied over that into the fourth. So in your calculator, just figure out what all this stuff is, and then take the fourth root of it. So here, just to show you how I would do it, first off, all that stuff on the left, we would do the 120 times the 2 to the 5th. Okay, that divided by the 180 times our error there, 0.0001. And I'd get an answer there. So that's all the stuff on the left-hand side, and we want to take the fourth root of that. There's a couple different ways to take the fourth root. I think the easiest way is just to raise it to the 1/4 power. Same thing as taking the fourth root. Great, and we get a number, 21.49. Now remember that our n here represents the number of partitions. The number of partitions cannot be a decimal. It has to be a whole number. And one thing I want to stress here, always round up. And for Simpsons, always round up to next even number. All right, so our final answer for this one's going to be 22. 22 partitions for this Simpsons rule to approximate 5x to the 4th to within, what is this, 10,000ths of a decimal. The reason this is very important is for computer programming mostly. So when you're writing up some kind of a program, you want your program to only do the minimum amount of calculations necessary. Otherwise, it would bog it down and it would slow down your program. So if you're making some kind of game or something like that for the phone, you only want your game to do as many calculations as it can possibly do or needs to do. Otherwise, it runs very slow. So if you only need this result to be within 10,000ths of a decimal, then you would only do 22 partitions intervals there. I know that this doesn't seem like you would need to do this for a game, but whatever your calculation is, this error estimate allows you to do the minimum number of calculations to get your answer to within the required amount. Okay, cool. So that is 8.7. Only one more section to go here for Chapter 8.